A brief history of time. Stephen Hawking. Chapter 1. Our picture of the universe. A well-known scientist, some say it was Bertrand Russell, once gave a public lecture on astronomy. He described how the Earth orbits around the Sun and how the Sun in turn orbits around the center of the vast collection of stars called our galaxy. At the end of the lecture, a little old lady at the back of the room got up and said, "What have you told us in rubbish way? The world is really a flat plate supported on the back of a giant tortoise." The scientist gave a superior smile before replying, "What's the tortoise standing on?" "You are very clever, young man, very clever," said the old lady, "but it's turtles all the way down." Most people would find the picture of our universe as an infinite tower of tortoise rather ridiculous. But why do we think we know better? What do we know about the universe, and how do we know it? Where did the universe come from, and where is it going? Did the universe have a beginning, and if so, what happened before then? What's the nature of time? Will it ever come to an end? Can you go back in time? Recent breakthroughs in physics, made possible in part by fantastic new technologies, suggest the answer to some of these long-standing questions. Someday these answers may seem as obvious as the Earth orbiting the Sun, and perhaps as ridiculous as a tower of tortoise. Only time, whatever that may be, will tell. As long ago as 340 BC, the Greek philosopher Aristotle, in his book On the Heavens, was able to put forward two good arguments for believing that the Earth was a round sphere rather than a flat place. First, he realized the eclipses of the moon were caused by the Earth coming between the Sun and the moon. The Earth's shadow on the moon was always round, which would be true only the Earth was spherical. If the Earth had been a flat disk, the shadow would have been elongated and elliptical, unless the ellipse always occurred at the time when the Sun was directly under the center of the disk. Second, the Greek knew from new travel that the North Star appeared lower in the sky when viewed in the south than it did in more northerly regions. Since the North Star rise over the North Pole, it appeared to be directly above an observer at the North Pole, but to someone looking from the equator, it appeared to lie just at the horizon. From the difference in the apparent position of the North Star in Egypt and Greece, Aristotle even quotes an estimate that the distance around the Earth was 400,000 stadia. It's not known exactly what length a stadium was, but it may have been about 200 yards, which would make Aristotle's estimate about twice the currently accepted figure. The Greek even had a third argument: the Earth must be round, for why else does one first see the sails of the ship coming over the horizon and only later see the hull? Aristotle thought the Earth was stationary and that the Sun, the Moon, and the planet and the stars move in circular orbit about the Earth. He believed this because he felt, for a mystical reason, that the Earth was the center of the universe, and that circular motion was the most perfect. This idea was elaborated by Ptolemy in the 2nd century AD into a complete cosmological model. The Earth stood at the center, surrounded by 8 spheres and carried the Moon, the Sun, the stars, and the 5 planets known at the time: Mercury, Venus, Mars, Jupiter, and Saturn. The planets themselves move on smaller circles attached to their respective spheres in order to account for their rather complicated observed phases in the sky. The outermost sphere carried so-called fixed stars, which always stay in the same position relative to each other, but which rotate together across the sky. Far away beyond the last sphere was never made very clear, but it certainly was not part of the mankind's observable universe. Ptolemy's model provides a reasonably accurate system for predicting the position of heavenly bodies in the sky. But in order to predict these positions correctly, Ptolemy had to make an assumption that the moon followed a phase that sometimes brought in twice as close to the Earth at the other time. And that means the moon ought sometimes to appear twice as big as at the time. Ptolemy recognized this flaw, but nevertheless his model is generally, although not universally, accepted. It was adopted by the Christian Church as the picture of the universe that was in accordance with Scripture, for it had the great advantage that it left lots of room outside the sphere of fixed stars for heaven and hell. A simpler model, however, was proposed in 1514 by the Polish priest Nicholas Copernicus. At first, perhaps for the fear of being branded a heretic by his church, Copernicus circulated his model anonymously. His idea was that the sun was stationary at the center at the Earth and the planet moved a circular orbit around the sun. Near a century passed before this idea was taken seriously. Then two astronomers, the German Johannes Kepler and the Italian Galileo Galilei, started publicly to support the Copernican theory, despite the fact the orbit it predicted did not quite match the ones observed. The death blow to the Aristotelian Ptolemy theory came in 1609. In that year, Galileo started observing the night sky with a telescope, which had just been invented. When he looked at the planet Jupiter, Galileo found that it was accompanied by several small satellites or moons that orbit around it. This implied that everything did not have to orbit directly around the Earth, as Aristotle and Ptolemy had thought. It was, of course, still possible to believe that the Earth was stationary at the center of the universe and the moons of the Jupiter moved on extremely complicated paths around the Earth, giving the appearance that they orbit Jupiter. However, Copernicus' theory was much simpler. At the same time, Johannes Kepler had modified Copernicus' theory, suggesting that the planet moved not in circles but in ellipses. An ellipse is an elongated circle. The prediction now finally matched the observations. Okay.